I illustrated by using this structure, the undoped cubic structure about lanthanum manganese oxide. And here it's very important and it's very clear, the manganese O6. By somehow I will focus on it, and I calculated some important result about the bond length, manganese oxygen bond length, and manganese oxygen manganese bond angle. Okay? I selected lanthanum, it was belonged to rare earth, and the other doping element, calcium strontium, were belonged to alkaline earth. Here, let me talk about sol gel, why I selected this chemical process. Here, from this simple diagram, it's very clear. It's increased, how many used number is increased too much from last 10 years, more than 1,500 to another research by using this sol gel to produce why this used number is increased continuously, because it has some great advantage. Let me talk about them. First, let me say from this advantage are the purity, uniformity, and full control on particle size. It could be from 10 to 100 nanometer, environmentally friendly, not toxic, let me say, easier to acquire. It can be done approximately to 200, or maybe, yes, approximately at 200 or 220, easily to scale up. But like any method in our life, it has another black side, the disadvantage. The most two important disadvantage are sensitivity to moisture, because that I used foil aluminum to protect my structure, and hard to scale up, and let me inform, don't forget it's consuming time. And the last important disadvantage is creating fractures. By that, I used gelating agent to prevent these fractures, and I will explain more in next slides. Here, the steps, step by step, about the sol gel, how I used it. It's contained from 5 steps: hydrolysis, condensation, aging, drying, and calcination. Here, the exerogel, how it was like a foam, and at last the final product. I will explain all of that briefly and at next slides. Here, let me start from hydrolysis with the inorganic metallic oxide, or let me say the precursors: lanthanum oxide, strontium nitrate hexahydrate, calcium nitrate hexahydrate, manganese nitrate hexahydrate, with some amount of water, hydrochloric acid, and let me don't forget the most important thing is the agent element, citric acid and ethylene glycol. Each one from them, it was a specific amount with crucial mathematical function. Okay. Here, I was here. I worked on all of them by using this scalar, this tube here, by calculate how much I need from hydrochloric acid. Let me talk about the condensation here to form sol by polymer network to make the metal oxide linkage. That's me. Here I have sol, and I use this thing is we can say it's a magnetic fish, and is the stirrer device. Can stir the liquid, and at the same time I can use it as a furnace by increase the temperature. I started from 100 Celsius and increased step by step to reach my specific degree. Okay. Here, step by step from 100. When the stirrer device started and increased the temperature, I noted increase the liquid by the color, the viscosity. Here, increase the viscosity of the solution. That's mean.
So, Ali, could you please be faster with the...
Okay.
Okay, that will be better.
Okay, here I have polymer network grows. That's mean I made the gel. Here, aging, the gel precipitation network will happen. That's mean the porosity decrease and thickness is increased. Here, it's be like as honey. The magnetic fish, it's very difficult to move on it, okay? Drying, it's very simple process. By using this stirrer, I increase the temperature more and more. When the liquid is removed, here, let me say why I use this drying simple process to evaporate the liquid. I made it, I put it at first. I'm talking about hydrochloric acid and the water, the solvents. Because I will use another thermal, I use another furnace, okay? Here, the calcination, by use this furnace, not the bigger one, okay? Calcination to dry, to evaporate the aging process, the aging element, I mean citric acid and ethylene glycol, by increase the temperature more and more to reach 600 CZ to a few minutes. Here, I use this mortar to two purposes: to eliminate any possible accumulation and to decrease the grain size of the nanoparticle. After that, I have homogeneous powder. By using this pressure, I made my belts with 1 cm and have thickness. Okay? I use different sintering temperature to can illustrate very well the act about the thermal degree on all of these structures. Actually, to 72 hours, because the how much degree and the time is very crucial to us. I left it to 72 hours to reach the 27 Celsius, like the room temperature, okay, to can deal with it. I have 12 belts instead of 18Y, because at 1300, the bolts are melted, because like we know, any structure has a melted temperature. That means I increased the boundary, because that I lost it. Now I have 12 belts. Let me talking about the X-ray diffraction. It's the device contained from the source, the detector, and put it the belts here. Here, by X-ray diffraction, that means the X-ray waves will diffracted. That means I have constructive and I have destructive. The peaks will contain from constructive, okay? Here it's clear, here it's constructive, that means the wave will be bigger, and here will be like destroyed because it's out of alignment.
Ali, you have 10 minutes to finish the presentation.
You told me 40 yesterday,
no,
not 20.
20.
Yes, like what? I'm happy when I was talking.
All right.
The atomic appliance here is very important. It acts like a slides. Because that I have peaks, okay? Atomic appliance acts as a slides. The constructive interference defined by Bragg's law, lambda equal to d sine theta. Here, wave number 1, wave number 2. By using match program to calculate the crystal structure and rotovolt refinement, it was a function in foolproof software to calculate the peak shape, unit cell dimension. ABC is very important in my work. because one of them or most of them will distorted, someone of increase, someone of decrease, we will see in my result. And the coordinates. Let me, okay. To calculate lots parameters, particle size, and strain. Full proof used Thomson-Cox Hastings to refine the peak shifting and broadening. Of experimental data, don't forget Williamson helped out to calculate the average of particle size and strain to all of my peaks. Here, some of my original plots. By using the original, by taking the data from Vesta, I plotted these diagrams. Let me say, for example, at lanthanum calcium manganese oxide at 1 molar ratio 900, I have these two lines of peaks. The first one reflect or is talking about the mine structure peaks. The second line talking about the impurity peaks. Here at 5 at the same degree, I have just one line. That's mean I have a pure structure with single phase without impurity. Is interesting. Here, we're talking about the peak basically depends on crystal size and lattice strain, because when the particle size is increased, the peaks will be sharper and sharper. Here is another interesting original plot. Here it's talking about more lines about impurity, because here I have two impurities, not just one. By that I illustrated, I used a summary to my result about the particle size at 1 molar ratio. It was the bigger one when I increased the temperature from 900 to 1100. All of these at lanthanum, calcium, manganese, all the particle size is increased, but with different ratio by increasing the temperature from 100 to 1100. And the volume, the unit cell volume, don't forget it, all of these are increased with different ratio by increasing the temperature. That's affect the temperature. Increasing the temperature is very important. Here now I'm talking about lanthanum centranium manganese oxide. Here I have some unexpected, because the particle size at 900, it was more than 1100, is increased. But at 5 molar ratio, it acts like normally behavior, is increased from, when you increase the temperature from 900 to 1100. Here, it's some different from calcium doping. The volume, like I expected, all of these are increased. Now it's a summary. Lanthanum calcium manganese oxide, in my opinion, it was better, because I have, when you increase the temperature, I have ideal angle, 180, okay? At the same time, the manganese oxygen bond length is increased a little bit. The temperature increased, average particle size is grown, like I illustrated in the previous plot. Lanthanum 5 molar ratio and 10 at the 900 CDZ, it was interesting because it was single phase without impurity, better than 1 molar ratio. Crystal system of impurity is changed from tetragonal to hexagonal at 1100 CDZ. At lanthanum centranium manganese oxide, the angle, it was good, it was big, but not like as centranium doping. It reached 180. At 900, 1100, the angle is decreased. Bond length is reduced at 10 molar ratio, it's good. Particle size of the 5 molar ratio 900 CDZ is biggest at it reached 1600. It's interesting. And strain was minimum at when you increase the temperature, 2100 Cesium at 10 molar ratio. Don't forget the important thing at centratium as doping element at 10 molar ratio, bigger in temperature. I had 2 impurities, that's mean 3 phases. At centratium 10 molar ratio, low strain. At 900 10 molar ratio, the biggest angle, but is the smallest as last bigger particle size. And don't forget, I noted important thing in the plots, the particle size, it was almost at 1 molar ratio, the bigger, but at the same temperature. At the same temperature, 1 molar ratio, it was the bigger, but when you increase all of these, approximately is increased. That's it. The future dope work, I think, this will be better and work on new doping agents. For example, instead of strontium, barium, and work more on synthesis techniques to further refine the properties to can reach better properties. That's it. Any question? I wanted to talk more, to illustrate more, but the time it was not big. I don't know if he hear me or not.
Haydar şey yapabilir mi? Öğrenci sunumu bitirdi.
Evet, izledim. Evet.
Sorulara geçelim. Evet.
Yavuz çıkartabiliriz o zaman. Evet, sorularla devam edelim. Sorulardan sonra çıkartacağız. Sorularda da çıkartacağız.
Öyle mi? Tamam.
Yavuz sen alamıştın.
Why he is leaving us?
It's the rule.
Oh, okay, I got it.
Haydar hocam başlayayım ben.
Evet.
Ali, thank you for your presentation. The first thing I talked about, you have some different label for your compounds. Can you open any page of your presentation?
Okay.
Yeah.
For the labeling the compounds.
Yeah. LCMO. Yes. Sometimes you use LCMO 10, 5. What's the meaning of this? You didn't say anything about.
At first, at the first column in my thesis, I illustrated.
You have to say something. Your presentation. I read your thesis, but there is no problem. But you have to say something here.
So,
Because I depended on, I illustrated that in my thesis, okay? I can illustrate it again. 10, that's mean 10 molar ratio. I'm talking about the aging element. I'm talking about the citric acid.
You have to say in your presentation. You have to say.
Okay?
Yeah.
Like you want. If you want say that again, I will be happy.
No, I know.
Okay.
But you
Like
have
you
to
want.
so at the beginning, you should have to explain that this sample refers to that one. This one is refers to that one. So if you are talking about LCMO, which means that this is something here. But what about the LCMO? So can you tell me the preparation? Yes.
This
What
is
is-
lanthanum,
Yes.
calcium, manganese, 3 oxygen.
So, okay. But what is the, so is it 1, 2, or 10? 1, 5, or 10?
Yeah, you know, there's a student here and he knows anything about your thesis. So you have to say something. This is this and this is this.
So what, I think that, let's say,
Here,
that
at
you
the
have no,
conclusion,
you have no LSMO particle, I think, is it? Do you have?
what hocam?
Do you have LSMO, LCMO as a sample in your study?
That's mean lanthanum.
Parent sample is LCMO, right? Your parents
LCMO.
Your parent compound, right?
Yes.
Yeah.
So-
What's the meaning of LCMO5?
Here I'm talking all the ratio.
You have to say
You have to say that one.
Yeah, so here
I didn't know that because I written all of this in my thesis. By that, yes.
Just we read all your history.
Okay, I get it.
But
the
you
other
should
people,
be, so the presentation should be clear. If you are talking about LSMO represents the all them. So all you have, you told us you have 1, 5 and 10 molar ratios, and this represents the SMO represents all of them.
Yes.
So from
this
900
temperature to
to
this
110.
Yeah.
So
Yes.
you should have to say that.
Because it's conclusion, that means it's the juice, the orange juice to all my results. Because that I was talking about all the molar ratio from this temperature to this temperature.
Okay, can you open the XRD page presentation?
What?
XRD.
XRD
Yeah.
presentation?
Yes.
Yes.
In
the
my
first
page,
page,
okay,
yes.
okay. With my
You
pleasure,
talk
yeah.
about the match program, yeah, and you say, I calculate, meaning.
From the beginning.
Yes,
yes,
yes.
What the-
I'm coming back.
Yes.
Yeah, okay.
This one?
Yeah.
Yes.
This talking about William Thompson,
Yeah.
Paul Claude.
Please read the first.
Like,
I use match
Yes.
to calculate, to
Just
determine,
wait here. Calculate or
to determine. It's better.
if you say calculate, I think it's mistake.
Yes, that's mean it's
You
a number.
have to try to choose a
Appropriate
suitable,
one?
yes, suitable structure to compare by using Rietveld refinement, right? So you can't say calculate,
Determine, it's better.
maybe.
Determine is better.
So
To
how can you use this program?
Uh,
Observation, better observation, any crystal structure with your compounds. Can
I-
you briefly say something?
How I use this
Yes.
program?
Yeah.
Match is a software program.
Put your sample values in this program, and then can you say something?
Yes, I take the data from X-ray diffraction.
Yes.
I put it in match. It was a long term, it was not easy. And I worked it by try to determine the appropriate crystal structure by depending on something like it was a library to suggest me to struggle me to can select the appropriate crystal structure.
Yes. Sometimes LCMO. Sometimes you can say trigonal. Sometimes orthogonal.
Yes,
What's the best choice for your
I
compounds?
worked on the CHI square. When my result is far away, the CHI square will be bigger and it's difficult to reduce it.
so you are talking about foolproof program now, I hear.
The the match are the same.
No.
It has the
Yes,
CHI
but
square.
it's, but only the values that they on the mesh program is only to observe whether it is okay or not.
Yes,
Yeah.
but CHI square helped me.
Yeah.
How did you put your secondary phases in the mesh program?
How I could find,
Lanthanum hydroxide, you have some impurities, right?
yes,
For your some compounds. How did you put mesh program? How can you choose this impurity phase by using mesh? What's your decision?
I had some buttons to change from phase number 1 and phase number 2. Phase number 1 and
Parent compounds, right?
Yes.
And second phase,
it was the
how did you
impurity.
choose? Lanthanum hydroxide or maybe lanthanum oxide, maybe metallic lanthanum?
How I
What's-
selected
do
the
you choose-
impurity?
Yes. What's your selection?
What's the criteria that you have selected?
At first, from many research, I expected my structures will be, some distorted will happen first from increasing the temperature. That means the crystal structure will change to tetragonal or hexagonal. This was two options. Maybe my result, my structures will be approximately one of them. First. Second, about how I could select the impurity. From many articles I read, the impurity approximately be tetragonal. We have many research before me. I depend on some of these research to can expect my results. How will be that help me to can select the, let me say, the correct results. Are you understanding me?
I understand you, but maybe you have manganese-based impurity phase, right?
Manganese?
Manganese-based, manganese oxide or any other,
Yes.
yeah. What can the reason for only lanthanum hydroxide? So there is a
Like
certain,
lanthanum chloride oxide.
yes, maybe, yeah.
Citric acid, I use citric acid like an agent. It's difficult to control on it. Approximately it's a result because I used the citric acid like an agent element. It's difficult to control on it. By that, I have lanthanum chloride oxide as impurity.
My question about ethical role, moderation and temperature. I have a question.
Yes, please.
You identified the 10 moles ratio as the optimal condition for enhancing the electrical and magnetic properties, right?
To enhance the
Yes,
properties, yes.
But you have any information about the magnetic and electrical properties for your compounds? How did you say?
I did a search. Hocam, every research have a goal. Okay, the first goal, it was to illustrate, to discuss my result. And after that, I was wondering, what after that? If angle is increased or decreased, what's the purpose from it? I did some search in Google. I found by increase the angle as kind as possible, that will be better. By decrease the manganese bond length as kind as possible, it's be better. Like I said before, when increase the angle to be, for example, in one of my results to be 180, it was ideal angle. That means the double exchange will be great.
And here's you can write, but you have an impurity phase. Is the problem?
Yes,
Or electrical
that's
magnetic-
decrease the properties.
Yeah. So you
Because
can't say enhanced
first-
magnetic.
Because that the first structure, it was at 5 and 10 molar ratio to lanthanum calcium manganate oxide, they were without impurity.
But
Because
you-
that I have,
But you can't say.
but
Most of the research
depending
article
on the
is
peaks,
contradictory results. So you can't say the magnetic and electric properties will enhance the due to your results. It's not correct, I think.
So,
Because you have any information about your compounds' electric and magnetic properties.
you haven't measured any electric and magnetic properties in your study, but you say it increases or decreases. So in order to say whether it is increases or decreases, you should have to make an electrical and magnetic observation, experiment and the result,
Yes.
and then say. But you may say that it may increase.
Yes, this is correct.
Okay? Or you may have literature finding that, and you can say that in some literature, as the particle size increases, so the magnetic properties
Still increase.
increases or decreases. But you say that magnetic properties enhances,
Yes.
and somebody looks at where is the magnetic properties in your thesis?
Yes, I
There's
didn't
no.
see it. So you can say certain
Yes.
information about magnetic and electric properties in your thesis.
But depending on angle and bond length
No.
The angle and bond length is not.
and the strain,
Yeah,
particle
no,
size.
no. There is other factors you have to take account.
There are so many factors.
Yes.
What about the impurity? So if you make a measurement on the magnetic properties, at the end you may have a contradiction to the literature.
Yes.
Maybe. So you say that if you make a magnetic property measurement due to impurity, so that you have so much impurity in your structure, and then your result may be contradict to the literature. But you may say that it may enhance. That's the key.
May
Yeah.
enhance,
May.
may,
Yes,
not
yes.
sure.
Not
No,
sure. You are not sure.
certain.
You haven't done it yet.
I
You
got
have no
it.
idea.
And I take this notes.
Yes.
It's very critical. You haven't done anything about electric and magnetic properties, but you say that it enhances or it decreases or suppresses the electrical conductivity.
What about my pure structure without impurity?
It's not important.
Does mean it's
Not
not
important.
interesting?
No.
Yes, it may be interesting.
But,
Every result is interesting. But
but you can say
you
certain.
can say that.
Yes.
Yes, the electrical properties increase. You can say after measurement, you will say it.
Electric properties depend on the grain size, grain boundaries, and other factors you have to take account. So you can say certain things about this. So
I get
you say sometimes particle size. How did you calculate the particle size by using XR data?
Yes.
Particle size or crystalline size or crystalline size?
Particle size or crystal size?
Yes, or
are the same.
crystalline? No. Not
Particle size, if we're talking about particle size,
Yes.
particle size,
Particle size is
calculated.
meaning of the grain size? Same?
no. Particle size,
I-
grain size are different. Particle size almost will be contained from one or more grain size. That's mean bigger.
I think most
maybe
of the
bigger.
articles use the crystalline size. You can calculate the crystalline size by using XR data.
Particle size calculated by foolproof, well, not by using X-ray diffraction.
There are
No, it's, yeah, sorry. You want to say something, but the particle size, the particle size is calculated with from the results of the X-ray diffraction.
But
And the Hippo also is the crystal
crystalline
size.
size, which of them correct?
Two of them is
Both of
correct. Two of them is
Yeah,
correct.
okay.
But we haven't calculated the grain size.
Yes,
Yes.
particle size.
You have to, if you have a grain size, I think you have a SEM image.
So we
Yes.
haven't done this.
So
Scanning,
you haven't-
electron
Yes,
microscopy,
yes,
that's
you
right?
you haven't got, so. you
Yes,
can-
I'm talking about just particle size.
Okay.
I talking about grain size, I talked on explaining the double exchange and how the grain size go out, go away from the boundary to make this grain be more suitable. Yes, I'm talking about that, but particle size is different from grain size. Particle size is calculated from foolproof, from
No,
Williamson.
from the X-ray
program,
diffraction. Full is a program. You may
Yes.
use another program also.
Yes.
You can calculate it.
It's
Anyway.
by using this function. It's different. It's different.
I have
Thank
one
you.
question. Okay. So I have one question. You are talking about the molar ratio. So what is it? Please, can you clearly explain us?
Yes, I have another PDF if you want.
No.
Huh.
Now you can explain.
The molar ratio,
What do you mean by the molar ratio?
one of the advantage on salt gel is full controlling on particle size. Like I said in the previous slide,
Okay.
they could increase the particle size from 10 to approximately 100 nanometer. That suggests me to search, let me say, by using the agent,
So the agent means, can you explain that?
agent,
What are
the
the agents?
ethylene
Glycol
glycol,
and
acetic acid,
Yeah.
all of these. By using these process agent element, it has two advantages. First one, to avoid the cracks, it could be done at my structure because the drying process, and by using it, I can increase the particle size to my perovskite oxide.
Okay.
That's mean when multiple my results were by talking about the how much mole I need from all the metallic element except the oxygen, multiple the how much I will use from ethyl glycol and citric acid, I will found a simple amount of particle size. By that, I use 3 different molar ratio by multiple these result of ethyl glycol and citric acid, multiple 1, multiple 5, multiple 10, and take and test the result to take a look which one will be bigger and how the
Okay.
result will be.
But I couldn't understand, or we couldn't understand how molar is coming from. Molar.
How molar come from?
Yes, yes. But how it's come from?